Hi, this is 9.05 Algebra 2, trying something new today. I am doing my video in the my video in the video, I guess. I don't know. Anyway, we are on 9.05, which is going to kind of wrap up our statistics unit for us at this point. And number 1 says that you're shown results of simulation that you tossed a coin 10 times and recorded the number of heads. You repeated that 50 times as shown in this graph right here. So if you counted up all of those little dots, there should be 50 of them. It says, based on the results of the simulation, which statement is false? Okay, so let's look at each of our choices and try to figure this out. Choice A, 5 heads occurred most often, which is consistent with the theoretical probability of obtaining a heads. Well, we know that the probability of landing on heads theoretically is 1 out of 2. So in this case, 5 did occur the most often, so that is consistent. So that's looking good. Letter B, 8 heads is unusual as it falls outside the middle 95% of the data. So let's find 8. Now, one thing that I want to emphasize that I haven't really to you yet is when you're asked to find a number like 8, said how many times the heads occur and it's 8, you always want to look at how many at 8 and for that entire tail. So let's just write that down. So always include the full tail. So for B, 8 or more. Sorry, that's really messy. Okay, so if it says 8 heads, we're looking at 8 or more, always the full tail. So if it's further to the right, then you take the right tail. If it's further to the left, then you take the left tail. Ours is further to the right, so we're going to take the right tail. So when I'm looking at this, now I want to figure out, does it fall within the middle 95% of the data? I'm going to count up my dots. So I've got 1, 2, 3, 4, 5, 6 dots over here. So that's 6 dots. So 6 times that we had this many heads, 8, 9, or 10. When we repeated this simulation 50 times right here. So 6 out of 50. So do that in your calculator. 6 divided by 50, multiply it by 100 gives us 12%. So 12% of the time, we got 8 heads or more. Is that within 95% of the data? Well, yeah, though when it would not be within 95% of the data, if it had been less than 5%, then it's outside of the 95%. So we're always looking for, if it's smaller than 95%, then that means it's outside the 95% of the data. It's unusual for that to happen. Could think 5%, a small percentage, unusual to get that. If you occur within 95% of the data, think bigger percent, not unusual to occur there. All right, so far this seems to be our answer, but let's look at C. C says obtaining 3 heads or fewer occurred 28% of the time. So now let's find 3 or fewer, which is here. Count up our dots, so there's 14 dots there. So for C, do 14 out of 50 and change that to a percent, and that'll give you 28%. And of course, you got to multiply by 100 in your calculator. So that's true. And then 7 heads for part D is not unusual as it falls within the 95% of the data. So, I mean, you can calculate that 7, and you want that whole tail again. So take 9 over 50. But we already know that in letter B, that's 8 or more was 12%. So as we get closer and closer to the middle, we're just going to stay within that 95% of the data. You're only going to be outside the 95% if you're on these, like way on the tails over here. Okay, so that is true as well. So the only one that's false is B. Number 2, we are going to skip. Oh, no, we're not going to skip it. Your number 2, there we're going to skip. On the sheet that you guys picked up from me in class, number 2 was multiple choice question. Actually, no, it wasn't multiple choice, but it was one that we already did. It was about the smartphone applications and finding the middle 95%, but we did that on the 9.04 notes, so we're not going to do it again. If you want to go back to that, you are welcome to go back to that video. So now we're going to go to what yours says is number 3 if you're using the older packet, and mine now says number 2. This is about Ava. So Ava designed an experiment to determine the effect of a new energy drink on a group of 20 volunteer students. 10 students were randomly selected to form group 1, while the remaining 10 made up group 2. Each student in group 1 drank 1 energy drink, and each student in group 2 drank 1 cola drink. 10 minutes later, their times were recorded for reading the same paragraph of a novel. The results of the experiment are shown below. So here's group 1. So group 1 drank 1 energy drink. And here's group 2, which drank 1 cola drink. 10 minutes later, here's how long it took them, how many seconds it took them to read that paragraph. So we're trying to see is, if you drink an energy drink, does it make you read faster? They gave us the mean of each group at the bottom here. Letter A says, Ava thinks drinking energy drinks makes students read faster. Using information from the experimental design or the results, explain why Ava's hypothesis may be incorrect. So good idea to pause the video right here. Kind of think about it. Think what's going on and why might her hypothesis be incorrect. All right, so maybe some ideas that you came up with is that looking through your data here, you may have noticed that some of these students had faster reading times in group 2. So, looking at 23.3, well, that's higher than all of the ones that had the energy drink. 22.1 is also higher. 24.4 is also higher. 21.2, 21.2. None of these even get up that high into the past 20 seconds. It looks like the highest here is 19.7. So one reason why it could be incorrect is that group 2 has some students, and actually quite a few, so maybe even several students that read faster than students in group 1. You might also say something about that the groups are really small. There's only 10, I think it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there's only 10 people in each group. And that's small for a study. So the more people you have, the more accurate your data is going to be representing a certain population. Using the given results, Ava randomly mixes the 20 reading times, splits them into 2 groups of 10, and simulates the difference of the means 232 times. So here's where we're going to start talking about something kind of different, and that's this simulated differences model that we're going to look at. What is happening here? And I'm just going to write it down because I think it's important to be able to go back to it and figure out what what are we doing, just to kind of wrap your mind around all of this information. So let's just write out here how to find the simulated difference model. So what we do is we would take all of the data that we found. So we record all the data for how long it took for each of them to read their paragraph. Record it just like she did. Then what you're going to do is you're going to put each time, and this is like the way to do it without a computer, because obviously it's going to be a lot easier if you have a computer and you can make it faster and you can do a lot more simulations and re-randomizations. But just so you get the idea of what like a computer would be doing, we're going to put each time, so each person's time, on a separate card. So like on a note card. Okay, so we took all our note cards and we write out what their time was. Then we're going to take all those cards and we're going to shuffle them together. So it doesn't matter what group you are, you're going to be all put together and shuffled into one big stack. Then you're going to take your cards and you're going to sort them into two different groups. Sort into two groups. So we're not basing it on if they had an energy drink or a cola drink anymore. Right now, we're just re-randomizing all the data. And the reason we're going to do this is we're hoping to figure out is when we get a difference in our means. So one group seems to be outperforming the other group. Is that just due to chance and it just happened to happen that way? Or is it due to something more? Is it maybe due to the energy drink itself? So we sort them into two groups. Then what we do is we find the mean of each group. In these random groups that we made, and then subtract those two numbers. Because difference means subtracted. So you're taking the two means and subtracting them from each other. So we're subtracting the means, finding the difference of the means. And then in this case, we're going to do this 232 times. So we're re-randomizing it 232 times. And what that will do is then we would plot all that information out. And we'd see, okay, well, how many times did a difference of the means occur? And we're going to look at our specific difference in the means then. Now, when we talk about these difference in the means models, in order to be statistically significant, and actually, you know what? Let me show you what it means. Let's find the difference in our means first. So part B says Ava has decided that the difference in mean reading times is not an unusual occurrence. Support her decision using the results of the simulation. Okay, so if you look back on the last page, group 1 said had a mean of 17.7, and the group 2 mean was 19.1. So they asked us to find the difference in the means. Difference in the means. And it tells you right here that you want to do group 1 minus group 2. So you want to make sure you do what they say to do. So we're going to take group 1 minus group 2. So that gives us our negative 1.4. as our difference in the means. Okay, so now we did this whole process. So now we would do this to get this graph right here. We would write all our data on these note cards, shuffle them all together, sort them into two groups, find the mean of each group, subtract them, plot it on our graph. Then we do it again, write them all on note cards, shuffle them all together. Well, we already wrote them on the note cards. Shuffle them all together, split them into two different groups, find the mean of each group, subtract them, plot it on our graph. And then eventually we end up doing that 232 times, and this was the graph that we got. So it's, again, as you do more and more of these, it should start to look more and more normal, meaning that nice bell curve. Okay, so we found our difference of the means to be negative 1.4. So we want to know, is this statistically significant? So if negative 1.4 occurs often, so within, and we have to define often because we all have different ideas of what that might mean. If negative 1.4 occurs within the 95% of your data, then that would be very common to happen, right? That would be not unusual. So if it occurred less than 5% of the time, so it's on like the ends of the tail, one of the tails, then that tells us that, yeah, it is unusual. That didn't happen very often. So if it didn't happen very often, we'd say it's statistically significant, and that it may have been due to the energy drink. But we can definitely say that it's probably not due to just chance, because it occurred so few times when we made them completely random. Because when we're plotting all this data, we're not dividing it up anymore between whether they drank cola or if they drank the energy drink. We're just putting all of them together and sorting them into two groups. So it's no longer based on those drinks that they had when we find these differences. So that's why we're doing that, to really see if our result is valid, or did it just happen because when I take any group of kids and I divide them into two groups, I often get that difference in the means. So now let's find negative 1.4. So down here on the bottom, you can see each bar is like between the two little marks. So I'm going to go back. This bar right here is negative 1.6, so 1.5. And then right here, that would be negative 1.4. So that's this whole bar right here. Okay, the one that's at 3. And again, like I said, you want to take the entire tail. So I want to take from 3, it's on the left side of the graph. So I'm going to take this entire tail. Always take the entire tail. Okay, so now I want to find if this is not an unusual occurrence. Okay, so I'm just going to, before we do that, I want to write out how you can tell if it's going to be statistically significant. So to be statistically significant. So it means something, is what statistically significant means. It's important what you concluded. In a simulated difference model, you want it to occur less than 5% of the time. Less than 5% of the time, because then it is probably not just due to chance, your outcome. So if it is occurring fewer than 5% of the time, it didn't happen very often when you made all of those simulations. And so there may be some statistical significance there. All right, so we found our difference in the mean to be negative 1.4. Now I want to add up all of these little bars. So this one, let me make the center again, is 3, then 2, 1, 2, 3, 2, 2, 5, 1, 1, 2, 1. We add those up together, and that gives us 25 times. So 25 times out of the 232 times that we simulated it. And that, you can put that right into your calculator. gives us 0.1077. Okay, so approximately multiply that by 100 or move your decimal, about 10.8%, let's say. So again, you may want to make yourself a note here at negative 1.4, always count the entire tail. So you want negative 1.4 or less. All right, so negative 1.4 or less occurs 10.8% of the time. So if it occurs 10.8% of the time, is that less than 5%? No, it is more, which means it is within your 95% of your data. So it is not that unusual for it to happen, which means it is not statistically significant. Okay, so support. So she says, decide the difference in the mean is not an unusual occurrence. Support it and explain your reasoning. Okay, so we're going to say the difference at negative 1.4 or less occurs about 10.8% of the time. Of the time in the simulation. So it still doesn't like my vertical lines here. It is not, and horizontal apparently, not an unusual occurrence because it is not less than 5% of the time. So that's the key you're looking for here. Meaning it would be within (95% of the data. So again, think within 95%, that's the majority of the data. That's very common for it to happen. Less than 5%, it means it's on the tail. One of the tails, it means it's not occurring very often. So it would be an unusual occurrence then. And you want to just keep those big ideas in mind, that if you're in the 95%, you're in the, larger part of the data, 5%, it's not as common for that to happen, because these questions ask different things sometimes. Last time we were just asking you, is it within the 95% or not? Is it like they were doing, how many colored candies were in the bag? And we wanted to know if it was what they had claimed was going to be. Where now we're looking at a study, a different type of study, saying we want to see if this drink is improving their test scores, or is it just random that might happen? So they're different types of problems, but they're all based on that same idea of the 95%. And if it's unusual, then it's occurring less than 5% of the time. And again, these are all Regents questions. I don't know if I told you that yet for these. So the next one is two different types of music are played while taking a quiz. We want to see if there's a relationship between the type of music and their grade. So 16 students were randomly assigned to either a room softly playing classical music or a room softly playing rap music. The results on the quiz were as follows. Here's your classical grades and here's your rap grades. John correctly rounded the difference of the means of his experimental groups as 7. How did John obtain this value, and what does it represent in the given context? Justify your answer. So how did he get a difference in the means? Well, he found the mean of each group. So you have two options. You can go to your calculator and you can do stat edit and then stat calc number 1. And you can do that for each of these lists, or you could type in all the 8 numbers for classical and then add them up, divide by 8, and do the same thing for rap. I don't care how you do it. but I would like you to verify that he got 7 as difference in his means. So pause the video, try to find the mean of each of these different groups. Okay, so I found the mean as well. And for classical, I got 82 for the mean. And then for my rap, I got 74.625. So I want to find the difference of the means. I'm going to take my 2 mean values and subtract them. And when I do that, I got 7.375. So this says, first question is, how did John obtain this value? So this is good because that's approximately 7 if I were to round it. All right, so let's say how we got it. So John would have found the mean score for each group and then subtracted those 2 numbers. Subtracted the 2 numbers. That's how we got it. What does it represent in the given context? So in this context, it tells us that the classical group don't know what I'm spelling here. The classical, there we go, group's mean was 7 points higher than the mean score of the rap group. So in other words, on average, the classical group scored about 7 points higher than the rap group. So you don't have to write more than that. That would be acceptable for your answer. But just as you guys are starting to learn this, I'm just going to give you some other words to help it all make sense. So on average, the classical group, because they had a higher mean, right? About 7 points higher. The classical group scored about 7 points higher than the rap group. So just other words to help you understand this. And sometimes you may have to go back and listen to this multiple times or write it down and then read it multiple times just for it to kind of make sense and wrap your brain around it. All right, so to determine if there is any significance in this value, John re-randomized the 16 scores into 2 groups of 8, calculated the difference of the means, and then simulated this process 250 times shown below. So altogether, if you count up all those dots, there should be 250 of them. So what did he do again? Well, he wrote down, or he may have used a computer, but if he wasn't, he would write down each of those scores on a separate note card. So 74 on one card, 83 on another, 77 on another 77. And he would write down all 16 of those scores. Then he's going to shuffle them all together. He puts them into a stack, and then he sorts them into 2 piles, 1 in each pile. And then he goes back and forth until he's done all 16. Then he takes 1 stack and he adds them up, divides by 8. Then he takes the other stack, adds them up, divides by 8. Then he takes those 2 numbers, subtracts them, writes it down, plots it on this little dot plot that you see below. Then he does that all again, takes all the cards, puts them together, shuffles them up again, sorts them into 2 piles, finds the mean of each stack, subtracts them, plots it. He does that over and over again, 250 times. And that's what we plotted right here. So say we got a difference in the means of -5. We plot that point. And for -5, we got it 1, 2, 3, 4, 5. I think there's 6 dots right there. 6 times we got a difference of -5. We got no difference in the mean, 0. So we got the same mean for each group, however many dots are in that column right there. The question says, does the simulation support the theory that there may be a significant difference in quiz scores? So is there a significant difference in the quiz scores based off of the music they listen to? All right, so let's say, what did we get for our difference in the means? We got 7. So we're going to go to our dot plot and we're going to find 7. So here's 6, 7. We take the whole tail. So take the whole tail. There are 4 dots in there. So 4 times out of our 250 times, we got a difference of 7 or more. So do 4 divided by 250, multiply that by 100 to find our percent, and it gives us 0.016, which is 1.6%. 1.6%. That's less than 5%. So if it's less than 5%, that's unusual. It didn't happen very often. It happened less than 5% of the time. So that tells us it is statistically significant. So yes, the simulation supports that there may be a significant difference in quiz scores because the difference of 7 occurred less than 5% of the time. So in other words, a difference of 7 does not lie within the 95%, is outside the 95%, that middle 95%. Okay, so yes, then there is statistical significance to this outcome. Okay, and number 4. And on yours, it's probably number 5, I believe. Joseph was curious to determine if scent improves memory. A test was created where memory is indicated by higher test scores. A controlled experiment was performed where one group was given the test on scented paper and the other group was given it on unscented paper. Our summary statistics are shown below. So remember, these symbols are if you have your sample statistics. As opposed to the population. So our mean for scented paper is 23, standard deviation 2.898, unscented 18, standard deviation for that sample was 2.408. Calculate the difference in the means in this experiment. So we're looking at the mean of scented paper, the mean of unscented paper. They tell us they want scented minus unscented, so that's 23 minus 18, which gives us 5. So the difference in our means is 5. A simulation was conducted in which the subject scores were re-randomized into 2 groups 1,000 times. The difference of the group means were calculated each time. The results are shown below. So clearly this was done on a computer. They found their difference of the means. They put all their data together, sorted them into 2 groups, found the mean of each group, subtracted them, plotted it, did it 1,000 times. And we want to know, using these results, determine the interval representing the middle 95% of the difference of the means. So this time, it's just a little bit different than the other ones we've done today. This one's more like the ones we did on 9.04, where they gave you the mean and the standard deviation. On the other graphs that we've done today, we haven't been given the mean and the standard deviation. So in order to find that middle 95% of the data, we want to take our mean and we want to add 2 standard deviations to it, just like we did last time. So 0.030 minus 2 times our standard deviation, 1.548. Then we're going to take 0.030 and add 2 standard deviations to it. That's going to go right into your calculator. And then it says here to round to the nearest hundredth. So negative 3.07 and 3.13. So to answer the question, the middle 95% of the data will be between negative 3.07 and 3.13. So it's still the same idea that if it's statistically significant, then it's going to be outside of that 95%. So it's still occurring less than 5% of the time. Is the difference in means in his experiment, I don't know where all these little lines came from, is the difference of means in Joseph's experiment statistically significant based on the simulation? Well, we got his difference of the means to be 5 earlier in the problem. So is 5 inside of this range of values? No, it's outside of that. So if this is your middle 95%, are we within that middle 95%? No, which means it didn't happen very often, which means it is statistically significant. So yes, the difference of the means is statistically significant based on the simulation. Because 5 does not lie in the middle 95% of the data. Because it's bigger than 3.13, which is your largest number within that interval. So having a mean difference of 5 would be an unusual occurrence, so it's probably not due to chance. And writing what we wrote here is fine, but I just want you guys to understand it, so just giving you a little bit more information. Having a mean difference of 5 would be an unusual occurrence. So that tells us it is probably not due to chance. Due to chance that there was a difference in the outcomes between the scented and unscented paper, which means it could potentially be because of the paper. Okay, so that concludes our 9.05 notes on statistics. And you guys will have a homework on doing some of these stat problems. And if you do have any questions, make sure you let me know, or we can set up a meet. And that's it. I hope you have a great day and stay healthy, love math, and pie out.